My dear friends, welcome to SEKAR classes on applied data science with Python. This is lecture number 234. In this lecture, we will try to understand limitations of PCA, that is Principal Component Analysis. Before discussing this particular concept, let me spend few minutes on eigenvalues. We discussed geometric interpretation of eigenvalues and eigenvectors in our previous lectures. Let me spend few more minutes on eigenvalues. Eigenvalues are used to see how data is spread. How data is spread. For that we discuss few cases, isn't it? How data is spread. What does it mean? Whether the data, how data is spread means whether the data is spread. Data is spread on one axis or other axes, isn't it? Or other axes too, isn't it? This is the basic concept behind eigenvalues. I can interpret eigenvalues like this also. Let me say like this. We can also use these eigenvalues the other way around. If we have to preserve if we have to preserve 80% of the information or variance, 80% of the information, 80% of the information, and accordingly we need information, and accordingly we need to find least possible dimension k, with which we can preserve we can preserve 80% of the information. 80% of the information. What does it mean? 80% of the information means 80% means what? 80% means 0.8 is equal to lambda 1 plus lambda 2 plus so on lambda k, isn't it? By sigma I equal to, let me say there are n eigenvectors. Let me say lambda I, isn't it? Here we need to find least possible value of k. What we have to find? Least possible value of k. That's the concept. Least possible value of k for which this equation holds true. If you are able to find such k, I can say I can preserve 80% of the data. Anyway, in future classes, I will apply this concept so that you can understand. Now, we will try to understand limitations of PCA. First, let me take one simple case. What is this simple case? What is, let me assume, this is my data distribution. My data distribution is circular fashion. I can say this distribution is known as circular distribution. This distribution I already discussed in my previous lecture, where lambda 1 equal to lambda 2 data is just like circular distribution. In this PCA algorithm, what happens here, in this case PCA algorithm fails to find the best access, upon which spread is maximum, isn't it? Spread is maximum. This is because an axis that makes any angle with x-axis, isn't it? I will repeat. Because an axis that makes any angle, with x-axis gives the same variance, I can say it gives the same variance, isn't it? Because hence PCA fails. What does it mean? Let me say like this. PCA fails means, let me repeat this concept. Otherwise, suppose if my data set looks like this, of course I only look at 2D. I am looking at 2D, isn't it? Because it is easy to understand. Suppose if you want to project data, my intention is I have to project data from 2D to 1D. That's my idea, isn't it? Let's assume my data set looks like this. This is my data set, looks like this. Let's assume this is my V1. Let me say this is my V1. Yes, this is my, let's assume this is my V1. If I try to project onto this, I am going to lose lot of information. If I keep on projecting all data on this axis, I am going to lose lot of information, because this is just like circle, which means my lambda 1 is roughly equal to my lambda 2, isn't it? They are going to be very, very close. This lambda 1 and lambda 2 are going to be very, very close, which means if I project all of my points on V1, what happens? The information lost, the information spread lost is very high. If I keep on projecting all these points in this particular, on this line, information lost is very high, isn't it? I have to do it. If I have to do it, I'm forced to convert data from 2D to 1D. I have to lose lot of interesting information that I am throwing away, which is unfortunate. So if you have a data like circle in 2D, it is a circle. What happens in higher dimensional spaces? It may be sphere or hypersphere. If your data is distributed like sphere or hypersphere in high dimensional spaces, PCA will not do good justice. PCA will not do good justice. PCA will not do good justice. It cannot do good justice for circular shape of data or sphere type of data or higher hypersphere type of data, because we are going to lose lot of information. I already discussed in my previous lecture, lambda 1 by lambda 1 plus lambda 2, we were getting something like 3 by 6 means 1 by 2 means you are able to only 50% data you can able to retain, isn't it? You are losing a lot of information. If you try to project the data from D dimensional to D dash dimensions, such that your D dash must be less than D. In that case, you are going to lose lot of information. estimation. This is one case where PCA algorithm fails. I need not repeat this again and again. Why? Because this is already discussed in my geometric interpretation of eigenvalues and eigenvectors, that case 1 is related to lambda 1 equal to lambda 2 case, where we were losing 50% of data, isn't it? It's simple thing. This is another case in this direction. Let me say this is in this direction. Yes, in this direction there is a maximum spread. In this direction there is more spread. Then this direction, my second direction is, where is my second direction? Let me say this is V1. My second direction is something like this V2, isn't it? This is my second direction. Let me say this first one, this one is V1. Let me say this one is V2. If I start projecting all the data, if I start projecting all this data here, all these points, these are different points. I can keep on projecting all this data like this. If I keep on projecting, what happens? They will form two different clusters, isn't it? Still they will form. What happens here? You notice you have four groups. This is group 1, group 2, group 3, group 4, isn't it? Here you notice that there are four groups or cluster points. We call them as clusters. There are four groups. These are four distinct groups. I project all the points. If I project these points here, this point, this point, this point, like that. Again, if I project these points here, what happens? If I project these points, even projected points forming groups, you will get two clusters, isn't it? In similar manner, if let me say I am projecting all the points on V1. What happens if I keep on, when I project all the data onto V1, all these points will be projected here, all these points will be projected here, all these points in similar manner, all these points will be projected here, all this means this in this region only this group points will be projected. Why? Because I am projecting all the points on V1 axis. These points also will projected. Then what happens? These points will also get projected. Means this group of points will also get projected in the same region. These points forming, actually this group and this group in 2 dimensions, they are forming good separation. These points forming good separated clusters in 2-dimensional space. They are projected in the, if I project this one, they are going to project in the same region. As these two groups are projecting in the same region, we are not able to distinguish them whether these are from this group or from this group. They are going to project in the same region. Now we are not able to distinguish them from this region or this region. For example, in the case of MNIST database, this data is related to maybe 3, this may be related to 2, this may be related to 3. If I keep on projecting, what happens? These two sets of points will all fall in this region, in the same region, isn't it? And terribly confused if actually saw this, if you see this data in two-dimensional space, there is a clear separation. Yes, there are two different cluster points, but if I project this data onto V1 axis, what happens? They are falling in the same region. Yes, they are getting crowded together. I can say all these points are getting crowded together, as we saw in our previous example of MNIST database. What did we see? We saw that zeros are well separated, zeros and ones are well separated. In the case of MNIST, just try to recall, these are well separated, isn't it? What happens for other digits? Rest of all them all are grouped together. So this is one case where you have difficulty. This is one drawback with your PCA. This is the case. This is a case. I can say this is second case. I can say this data is known as PCA may not work properly in the case of clustered, let me write, clustered distributions. This is clustered distributions. But what about first one? First one is, case one is circular distribution. In previous slide, this one is circular distribution. I have difficulty this one. This is circular distribution, isn't it? This is circular distribution, whereas this one is, what is this? This one is clustered distribution, isn't it? What is this? I have 4 clusters: cluster 1, cluster 2, cluster 3, cluster 4. This is known as clustered distribution, isn't it? What happens? This consider what happens here. There are, if you project the points upon the axis that is passing through large clusters, this is the point, this is the V1 which is passing through the large clusters. We lose lot of information. We lose lot of information. We lose a lot of information. We lose a lot of information of small clusters. Isn't it? If I keep on projecting all these things, they will come, they will crowd it together. We will lose some information here. If I keep on projecting, isn't it? When projected upon this axis, in the same way, we are going to lose a lot of information if you project a point on any axis. If you keep on projecting on V2 axis, this is about V1 axis. What happens if you keep on projecting points on V2 axis? Same thing happen. You will lose lot of information. All these information will be clustered here. Isn't it? That is the difficulty. In that case, these points will be projected like this. These points will be projected like this. Again, you will form 2 clusters here, but all these points will be crowded together. In both the cases, whether you project point on V1 axis or V2 axis, you will lose information of clusters. This is the difficulty. I can say this is case 2. Now we will try to understand case 3. What is this case 3? My case 3, I can say this is non-linear curves. This is just like a sinusoidal curve. Non-linear curves, isn't it? Non-linear curves. Unlike in linear distribution, in this case, if we try to find principal component that maximizes the variance over it, we would be losing. We would be losing the information. We would be losing the information and properties information and properties of that pseudosine curve, isn't it? How can I say? What does it mean? Imagine if my data set followed some sort of like, this is just like sine curve, isn't it? This is just like sine wave. So it has some interesting structure. These are my data points. 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 Let me say all these are my data points, isn't it? In that case, what happens? I have to find V1 by using principal component analysis. You know how to find V1. Now, if I keep on projecting all these points like this, if I keep on projecting all these points on V1 axis, what happens? You will lose this nice curve, nice sinusoidal curve, isn't it? You will lose some interesting pattern. So if it has some interesting structure, but now this, let me say, this is my V1, this is my V1, this is my V1, isn't it? I know how to find this V1. and this is my V2. Let me say this V2 is perpendicular to V1. Just 90 degrees to V1. Let me say this is V2. So if I project all of these points onto V1, just I am projecting all of these points onto V1, isn't it? I will lose this nice beautiful structure. I will lose this nice beautiful structure, isn't it? Sinusoidal structure, the sine structure in the data. I will never see this sine wave if I project all the data into V1. If I project all these points, if it is 2D, I have sine wave. If it is 1D, when I visualizing this data in 1D, I have lost all this information. These are some examples where PCA would fail. Just try to understand this lecture. This is one of the important lecture. If you have any difficulty, just keep a comment. Thank you very much.